Hi guys. So this is going to be our introductory video for our next unit, which is the work energy model. Um, Work energy model. The goals for this unit really I've tried to reduce them down to two things. One is to know what work is and to figure out how to calculate work values. My guess is that this is going to take about 2 videos to get through this. We're going to start it today, and then we'll pick it up in the next video as well. And then sort of the main focus of this unit is actually the second thing, which is to understand how work values, once you know how to calculate them, to understand how work relates to energy. And this is what we call the work energy theorem. And my guess is I think I could probably get through this in one video, but it could be 2 videos. So this will be 1 to 2 videos, just so you have some sense of how many video lessons are going to be involved in the course of this unit. So maybe we should just get started. I think I'm going to start big picture with the second bullet point here, trying to understand what work is. So we know a little bit about energy now. Our last unit, you'll recall, was about energy conservation. And so we learned from last unit, we learned that we have, in terms of mechanical energy, we have two types of energy. We have kinetic energy and we have potential energy. Kinetic energy abbreviated K, potential energy abbreviated U. Our equation, just to remember, for kinetic energy was 1/2 mv squared. And for potential energy, we thought about potential energy only as it relates to gravity. So that's gravitational potential energy, which we calculated as mg times h, where h is some height, you'll remember. So remembering that about energy, I want to think now about what work is all about. So what work is if an object has energy, has a certain amount of energy, and let's imagine you want to change the amount of energy that that object has. Well, to change the amount of energy, you have to do work to the object. So that's big picture. That's the relationship between work and energy. Work is equal to the amount of change in the energy of an object. So for instance, I happen to have my trusty bottle of hand sanitizer here. If I wanted to increase the kinetic energy of this bottle of hand sanitizer, I would have to do work to it. So for instance, I could throw it. If I exert a force on it, and we'll later on figure out exactly how to calculate how much work comes out of that force, but if I apply a force to the hand sanitizer bottle and throw it, it's going to gain kinetic energy. So in that case, the work that I did has turned into kinetic energy. I could also, by the way, I could do work and have that work turn into potential energy. So right now, if I take the bottle of hand sanitizer and I exert a force and thereby lift it up, if I increase the height of the bottle of hand sanitizer, then its potential energy value has increased. And so that's a case where I did work, and the work that I did, however many joules of work I did, all of those joules ended up in the form of gravitational potential energy in the bottle of hand sanitizer. So that's really big picture. So big picture. Work relates to the change in energy. As we'll see later on, we're getting a little bit ahead of ourselves here, but as we'll see later on, there are basically two types of work I could do. I could do what's called positive work, as we'll see, and I could also do negative work. Just to understand the difference there quickly, so that we have a sense of the big picture before we move on. If I increase the amount of energy, so as I did before, as if I lift this up, increasing the potential energy, or if I were to throw it, increasing the kinetic energy, that's positive work. So in general, positive work means that there's going to be an increase in the amount of energy in the system. In this case, the system is just the bottle of hand sanitizer. Negative work would mean somehow the force is decreasing the energy of the system. To think about an example of that, I might, for instance, drop this bottle of hand sanitizer onto my hand. And if I were to drop the bottle of hand sanitizer onto my hand, what is my hand going to do? Well, my hand is going to stop the bottle of hand sanitizer. So the hand sanitizer is going to have a certain amount of energy. Maybe if I drop it into my palm like this, it won't fall. If I drop it and then it lands in my hand, it had kinetic energy when it hit my hand, and somehow my hand reduced that kinetic energy. So the force that my hand exerted on the bottle decreased the kinetic energy of the bottle of hand sanitizer. So I'll do it again. If I drop this bottle, my hand will cause it to stop, thereby decreasing the amount of energy. So that's negative work. The negative work done by my hand decreased the amount of energy of the bottle of hand sanitizer. That's sort of a weird example, I guess. I'm thinking now, like if you were driving a car, if you hit the gas, you're doing positive work, you're increasing the energy of the car. You hit the brake, you're doing negative work, you're decreasing the energy of the car. All right, so that's big picture. Let's get into the details of how we would actually calculate work values. So let's see here, calculating work. Well, we already noted that in order to do work, you've got to apply a force. So it definitely has something to do with the amount of force that I'm applying. So if I take this bottle and I throw it hard, it's going to gain more energy than if I throw it gently. If I'm driving my car and I just give it a little bit of gas, it's not going to speed up very much. If I put the pedal to the floor, it's obviously going to gain a lot more energy. So it somehow has to do with force, for sure. But the question is, what else matters when we're calculating work values? So if I think about maybe the car example for a minute, if I were to hit the gas, but only hit the gas for over a short distance, then the amount of energy the car gains is not going to be that much. Whereas if I hit the gas and accelerate over a greater distance, then the increase in kinetic energy is going to be more. So the other thing that is going to matter for our calculation of work is distance. Over what distance is the force applied? So maybe to start with a very simple case, we could imagine the following. Let's imagine that there's a frictionless surface here, and I've got some block, some crate, box, whatever it is, and I come in here and I'm going to apply a force. And I'm going to apply that applied force. Let's say I apply a force of 50 newtons. And in applying that force, I move the box over a distance. So I'll say box moves. Let's say, we'll make life easy, we'll say the box moves 10 meters. Well, then the work that I do somehow relates to the amount of force and somehow relates to the distance. And for our purposes right now, our provisional definition of work, I'm just going to say the work done is equal to the force times the distance, F times D. So in this case, the work that is done on the crate here would be 50 times 10, which is equal to 500. 500 what, you ask? Well, since the amount of work done turns into energy, it might make sense that the unit is going to be the same energy unit, same unit that we had for energy, which is the joule. So the unit here is the joule, just as we had when we were discussing our energy unit. So this is like the most basic case. I apply a force, and that force is doing work, and I simply multiply the force times the distance. This is the simplest case. You might ask, is this going to be a positive work value or a negative work value? And maybe given what we just said, it'll be obvious to you that this is going to be a positive value, because the force I'm applying, what is it going to do? If this is a frictionless surface, that box is going to speed up. It's going to gain kinetic energy. So just again, to kind of get ahead of ourselves a little bit, this 500 joules is going to be turned into, in this case, it would be turned into kinetic energy. So I've done 500 joules of work, and that work has gone somewhere. It's gone into the kinetic energy. So under what circumstances might there be negative work? Well, think about it this way. What could be present in this situation that would cause the box to lose energy? And maybe it's clear to you if I ask it that way that there could be friction. So maybe now I'll go back and I'll imagine that there's friction here. Maybe I have a kinetic friction force here, and we'll say that that's a 20 Newton force. Just make life easy, nice round numbers. So now I could calculate if this was the work done by the applied force, I could now calculate the work done by friction. And that work is going to be 20 times the distance 10, or 200 joules. But I need to make that negative somehow. I need to somehow factor in that this is going to be a negative value. And again, just to reiterate it, I know it's negative because I know that that friction force, based on what I said earlier, that friction force is going to reduce the amount of energy. So now in this particular case, if I apply a force of 50 newtons and there's a friction force of 20 newtons, then you might wonder, what's the total work done? So again, this was the work done just by the applied force. This was just by the applied force, and this is the work done by friction. So if I wanted to now think about, okay, well, what's the total work then? The total work would just be the sum. It would be 500 plus negative 200, which would equal 300 joules. So in this case, where those 300 joules, where have they gone? Well, once again, they will have gone into kinetic energy. There's still a net force on this block, so it's still going to speed up. It's still going to gain kinetic energy. But now, since we added friction, it won't gain the full 500 joules of kinetic energy. It's only gaining 300 joules of kinetic energy. So that's kind of the very, very basic way we're going to calculate forces, or calculate work values. You take the force, you multiply it by the distance. Anytime, and maybe I should have made this more explicit, I'll do so now. What was the difference between the work value calculated by the applied force compared to the work value calculated by friction? Why is it that one's positive and negative? I mentioned that the work done by the applied force is positive because it increases the energy. But it might be easier, and this is quite true, it might be easier to note that I know the applied force is going to do positive work because the force is in the same direction that the box moves. So in this case, we were imagining that the box was moving in that direction. It was going to move to the right. So if the box moves in the same direction as the applied force, then the applied force will do positive work. In the case of friction, friction is pointing here to the left and the box is moving to the right. So if the force is opposite from the direction of motion, then that force will do negative work. To go back to the case of the hand sanitizer bottle here real quickly, if I were to lift this up, I am doing positive work. Incidentally, there's another force doing negative work, which you might have already picked up on, which is gravity. As I lift this up, I do positive work, but gravity's acting downward, so gravity's doing negative work. Likewise, or opposite, if I lower the bottle, now since I'm pushing up as the bottle goes down, I'm doing negative work now, and gravity is doing positive work. Because now the direction of motion is downward, gravity's pulling down, and so gravity, in this case, will do positive work, and my applied force does negative work. Going back to this example up here, maybe just to reiterate this, I could have noted, by the way, in this picture that we do have gravity, of course. There's some weight of the box, and there's a normal force. And since you might ask yourself, well, what work does gravity do? What work does the normal force do, right? The gravity and the normal force, they're neither in the same direction as the distance, right? The distance moved is this way, is to the right, it's going this way. So gravity is neither in the same direction as the distance, nor is it opposite. Same thing for the normal force. The normal force is neither in the same direction as the velocity, nor is it opposite. They're perpendicular. So how do I deal with that? Well, in this case, what we would say is the work done by gravity and the normal force is 0. So the work done by gravity and normal force are both 0. And the reason is because they are perpendicular. So now we know something, we're on to something here. We haven't really finalized the definition. We'll finalize the definition of work in the next video, but what we've learned here is that to calculate work values, to sum up now, you have to multiply the force times the distance, and you have to factor in the direction of motion. If the force is in the same direction that the object moves, the work value will be positive. If the force is opposite the direction of motion, the work value will be negative. And if the force is perpendicular to the direction of motion, the work value will be 0. Hope that was clear. In the next video, we're going to kind of take this discussion and we're going to finalize it into a full, complete definition of work. So I look forward to that next video.